right? I'll start sharing the screen and then we can get started with our fourth EM class. Uh, all right. Hold on. Okay. All right. So welcome to the Paragon X Electromagnetism class today. It's March 22nd, and it's going to be our fourth class of the EM series. So yeah, let's first review some of the homework problems. All right, first homework problem. Prove that if all charges on a conductor are stationary, the electric field at a point immediately outside a conductor is always perpendicular to the conductor's surface. Let's see. Sing, do you want to give us some of your thoughts on this problem? It's okay if you didn't do it, but uh, yeah, just any thoughts you have or any ideas, feel free to share them. Yeah, you can talk in chat. Yeah, yeah, don't worry. Yeah. So you can type in the chat what your thoughts on the problem is. And while we're waiting for Sing, how about anyone else if you have any ideas or like just start thinking about this question so that yeah. Uh Sing, all right. Don't worry, it's okay that you don't know. Um I'll just how about uh Kevin, do you have any ideas on how to do this problem? Why don't you share with us? All right. Then I don't think Kevin's responding, so I'll just explain the problem then. So we want to so for an arbitrarily shaped conductor, right? We want to oops, sorry. Uh, right. We have a conductor, so maybe it looks something like this. And then we want to prove that if the charges on the conductors, they're all stationary, then I want to find like I want to know that the electric field at a point immediately outside the conductor is perpendicular to the conductor's surface. So, okay, if all charges are stationary, so that means they're all stationary, right? Meaning that I cannot have an electric field that points along the conductor's surface. And the reason for that is, for example, if I have a charge over here and if the electric field, okay, if maybe a component of the electric field points like along the surface, so in that direction, then there will be an electric force, right? Because like you have that F equals QE, right? And if there's an electric force, it's in the direction of the electric field. The electric field is along the direction of the conductor's surface, meaning that the charge will be accelerated and it will move across the conductor's surface. But we can't have that happen, right? Because we're given that all charges on the conductor are stationary. So for that reason, all like if we have an electric field around the conductor, it has to be perpendicular to the surface. Otherwise, the charges will not be stationary. So that really just tests your conceptual understanding of what conductors are. And yeah, good job, Kevin. Yeah. If there were something, yeah, if the electric field was parallel to the surface, then charges would move along the surface. Yeah, well said. Uh, let's go on to the next problem. All right, consider a system consisting of a cylinder of radius R1 that has length L is much greater than R1, surrounded by a cylindrical shell with the same center and radius R2. Each cylinder has a charge Q, and part A is we want to use Gauss's law to find the electric field in the region within the shell but outside the cylinder. Uh, First, I'm just gonna draw a diagram for this so that uh you guys can visualize it better. So this is my outer cylinder, or yeah, sure. This will be my outer cylinder. This is my inner cylinder. Okay. The outer cylinder has a radius of R2. So I'll say like this this entire distance over here, that is gonna be R2. And then the inner cylinder has a radius R1. So this will be R1. Okay, and then each cylinder has a charge Q, so it'll look like Q over here and uh yeah, Q over here. G right. Okay, so using Gauss's law, find the electric field in the region within the shell but outside the cylinder. So we want to find the electric field in let me switch a color here, in this region over here. So like in that region. And so how are we going to do that? Well, so the problem wants us to use Gauss's law, right? And that's actually the best method we can do. So for example, if I draw a Gaussian enclosure, which will be a cylinder, so it's like a third cylinder, and its radius, shoot, it's like a third cylinder, and it's like in between the smaller cylinder and the bigger cylinder. And let's say it has a radius of has a radius of let's say it has a radius of r prime, right? Now I want to use Gauss's law, right? And remember Gauss's law, what does it say? It says that if I have an electric field, then the surface integral of like your electric field uh dot onto like an infinitesimal area segment, right? So that integral, that will equal to the enclosed charge, so Q enclosed divided by the epsilon zero, right? So uh, if we look at this situation, right, we have a cylinder that encloses another cylinder, right? And by symmetry, I also know that if I draw the electric field will probably look something like, or, or like at the position of where our cylinder is, it will be looking like we'll be pointing radially outwards, right? By symmetry, so uh, something like that, and so on, like all the way around the cylinder, right? And by symmetry, I know that the magnitude of the electric field, that doesn't, that's independent of like with a fixed radius, the electric field is the same. So like electric field here would be the same, like the magnitude of it would be the same as like the electric field here. So what that means is that when I'm doing the integral of E dot to dA, this E is constant over the entire surface. Also, notice that this E over here is always perpendicular to the surface. So what our integral really becomes is, it just becomes this. So it will be E and then not the dot product, but just the regular, you multiply by the integral of dA, right? And then what's that? Well, dA, that's just the surface area of a cylinder, right? So, okay, minusing if I don't include the surface area of the basis, so just the surface area of the like the side part of the cylinder. So that would be E times like 2 pi r and then times some length, right? And that equals to the Q enclosed over epsilon zero, right? And given that the cylinder has a charge Q, so it will be equal to Q uh divided by epsilon zero, right? Now, all right, so I get an expression for electric field. So E would be equal to be Q divided by 2 pi R 2 pi R L epsilon 0. And this is a function of R. So you can notice that the E is proportional to 1 over R. Yeah. And now let's move on to part B. So use, oh shoot, sorry. All right, use your expression for the electric field to find the potential difference between the cylinder and the shell. So basically what this is asking is that, okay, I know the electric field in this region, let me switch a color again. So I know the electric field in like this region of space, right? In between the two cylinders, well, like the cylinder and the shell, right? And now I want to find the potential difference between a point on the inner cylinder and the point on the outer cylindrical shell. Okay, so let me erase our previous work. So remember we got that E is equal to that should be Q over 2 pi R and then times big L times epsilon 0. Now we want to find the potential difference, right? So let's redraw the diagram. That's an inner cylinder. That'll be our outer cylinder. Now, this is the electric field in, it will be in like this region over here, or like anywhere in that region. So like in the region between the two cylinders. And then okay, I want to find the potential difference, right? So what's the potential difference? Well, remember we had that the potential difference V, right? That's equals to the negative of the integral of E and then dot onto some like infinitesimal like dr, right? Remember, this is a dot product, not just a regular product. So between these two vectors, and I want to find the potential difference between like here and here, right? So the simplest path I could do it would just be in a straight line. And the reason for that is because the electric field that's in the radial direction and my dr would also be in the radial direction, then this will be equal to just the regular like magnitude of the E and then just times the dr. And I already got the magnitude of the E, right? So it's just right over here. And if I want to find the potential difference between these 2 points, well, my integral would be, I'll do from the inner radius, which will be R1, to the outer radius, which is R2, and I do E times dr, right? So Q over 2 pi R L epsilon 0, and then times dr. And what this equals to, well, this will be equal to Q. It's just a simple 1 over R integral, so you'll be getting Q over 2 pi L epsilon 0, and then times natural log of, I believe, R2 over R1, and that should be equal to your the potential difference between the cylinder and the shell. So this will be your answer to part B. Right. And let's go on to part C, find the capacitance of the system. Okay, we already got our answer for V, right? And remember we have that for a capacitor, Q equals your C times the V, right? So your C would just be Q divided by V. And in this case, it would be equal to 2 pi, or C would be equal to 2 pi L epsilon 0, and then divided by natural log of R2 divided by R1. That should be your answer for part C. So that was it was a long problem, but it really goes over a lot of what we learned in the past few weeks. So if you ever want to review stuff, like from last week and also from the previous weeks, you should really mull over this problem and do it on your own and make sure you understand everything about it. So does anyone have any questions on this homework problem? If you do, feel free to shout it out or like send a message in the chat and I'll answer it. All right, doesn't seem like anyone has any questions right now. So let's go on to the next homework problem. I'll clear everything. All right, homework review number 3. A parallel plate capacitor is created by placing two large square conducting plates of length and width 0.5 meters facing each other, separated by a 1 centimeter gap. A source of potential is connected to the two plates so that a charge of Q equals positive sigma A is placed on the left plate, and a charge of negative Q equals negative sigma A is on the right plate, where sigma is 500 times 10 to negative 6 coulomb per meter squared. The potential source is then removed from the plates, and you'll see that this will be important later on. The plates are close together, so the electric field fringe effects at the edges are negligible. Draw electric field lines in the vicinity of the plates. Use Gauss's law to determine the magnitude of the electric field between the plates. Okay, so first off, we want to draw the electric fields, right, near the plates. So let's first look at electric fields that are not in the region between the two plates, so like outside of the two plates. Well, okay, so I'm given that so we're given the plates are close together, so electric field fringe effects at the edges are negligible. What this is just saying is that I can treat these two plates as infinite plates, right? So remember, if I had an infinite plate, how did I find the electric field? Well, I found the electric field by, I drew this Gaussian cylinder over here that enclosed like some region of the plate, infinite plate, right? And the plate had charge density sigma. Well, so the electric field would look something like this. So it'll be basically just like vertical, right? So like that. And also on the bottom surface, it'll be looking like that. And magnitude is equal everywhere. Well, so to find an electric field, how I did it was I did like, my E dot into dA, right? That would be E times, um, well, okay, there's flux through the top face and there's flux through the bottom face because electric field, it's vertical, right? And because the electric field is vertical, there's no flux through the side faces of the cylinder. So what this means is that my integral of the E dot onto the dA dot dA, what that becomes is it just becomes E times twice of the area of the basis, right? So E times 2 times pi r squared, and that should equal to the enclosed charge divided by epsilon 0, right? What's the enclosed charge? Well, I know the charge density sigma, right? So the enclosed charge will be sigma times the pi r squared, and divided by epsilon 0. And nicely, this pi r squared cancels on both sides, so I get E is going to be it's going to be sigma divided by 2 epsilon 0, right? Okay, now, so if I want to, wait, so this is what we got for the electric field. And by the way, it's independent of your distance from the plate, which is actually quite nice. Now, okay, if I look at a point over here, so it's external to the region between the two plates, right? Uh, okay, so if I look at the contribution from this positive plate over here, then what does the electric field line look like, right? So it will be pointing this way, right? Because it points away from the positive plate. And then I need to look at the electric field contribution from this negative plate over here, and that'll be pointing in the direction of that plate, so it'll be pointing this way. And because the electric field from infinite plates that's independent of your distance from the plate, these two vectors over here, which is like the vectors representing the electric field, they're both equal, right? And they're also in opposite direction. So what this means is that at any point outside of the two plates, outside of the region between the two plates, we have zero electric field due to the two plates. And now I want to look at the electric field lines in between the two plates. So I erase this, and to make it look, sorry, let's look at it closer I'll draw a side view. So this will be my first plate, and this will be my second plate, and this one's positive, and this one's negative, right? So if I look at a point, and just like some point over here, doesn't have to be exactly in the middle between the two plates. Okay, so if I look at the electric field due to the positive plate, right? Then Jacob, could you tell me what direction the electric field would be in? Like if I'm looking at this point over here and my two plates are surrounding it.
It would go towards the negative.
Yeah. So due to the positive plate, it will be pointing in this direction. And Jacob, what about due to the negative plate?
It would still point towards the negative.
Yeah. Exactly. And each of these vectors over here, which represents the magnitude, which represents like the electric field, right? Each electric field. So E due to each plate would be, for example, E positive, that will equal to uh the electric field to the negative plate. So E negative, and that would equal to sigma over two epsilon zero, right? And then, so that means that the total electric field, right, that'll be equal to sigma over epsilon zero, and it points from positive to negative. So if I look at a point over here, then the total electric field would be in that direction. It'll have magnitude sigma over epsilon zero. So draw electric field lines in the vicinity of the plates. Well, then if we want to draw the field lines, let me put that back on. I'll erase some of this. All right, we want to draw the electric field lines. Well, remember, so external to the two plates, we have no electric field. So the only electric field lines would be within the two plates. Now I know the electric field, it always points towards the left, right? From the positive to the negative. So the electric field lines would be looking something like this. So they're all perpendicular to the plate surface. I know it doesn't look like it, but okay, so this will be what the electric field lines look like. So yeah, pointing from positive to negative. And the magnitude, remember, the magnitude of electric field anywhere between the two plates, it's always sigma over epsilon zero, because I can treat the two plates as infinite plates. Okay, now let's go on to part B. Use Gauss's law to determine the magnitude of the electric field between the plates. Oh wait, actually we just did that, right? We did that, it was sigma over epsilon zero. So we also did part B. So let's go on to the next part. All right, calculate the electric potential V between the two plates. All right, so remember E equals to sigma over epsilon zero. And let's see. Uh Tony, could you remind us what the formula for the electric potential given the electric field? How would I write that? How would I write the electric potential in terms of the electric field?
Okay, so electric potential in terms of electric field.
Yeah.
Um, Wait, so like, what was the electric field symbol?
Like what the electric field is, or what do you mean? Like I
Um,
want to, yeah,
isn't it something like an integral of
yeah, yeah,
something
yeah,
like this?
yeah.
Is
Do you remember what was in that integral?
uh
Do you remember how to write the integral? So like v will be equal to the integral of something, right? And yeah,
like integral electric field
yep,
d length like what
yeah,
just understood this integral.
yeah, yeah. So what it is like I do the electric field and I do the dot product with an infinitesimal basically an infinitesimal like small length. So and it's actually negative on the outside. So for example, if I have an electric field that looks like maybe I have an electric field that looks like this, like I have a charge over here, so it has charge Q, electric field with lines, right? They look like this, uh like something like that, right? So in all the directions. And yeah, so this, this, right? And then if I want to find the potential difference between maybe, for example, this point over here, and if I extend this line over here, and this point, so if I I want to find the electric field, like I want to find the electric field at, sorry, I want to find the potential difference between these 2 points, right? And so I want to do the electric field and then the dot product of the electric field with like an infinitesimal uh, segment. And you need to notice that this is actually a vector. So for example, if I can choose which path I integrate on, this is actually a path integral. So like so that's why I have the vectors. It's not just a scalar integral. So for example, if I choose my path to look like I first go here, or let me use a different color. My path is I go from my starting point to there, and then I go from that point and I go over there, right? That'll be my path. Now, so on this path over here, right? What happens is like my infinitesimal length segment will be pointing along the direction of the path, right? So maybe in that direction over there. But my electric field, which I'll draw in red, my electric field would point in this direction. So when I do the E dot onto the DS, so the DS is pointing, wait, this is my DS, or hold on, let me switch to a better color. Uh, let's use blue. Okay. So this is my DS. Yeah, that's better. This is my DS, but my electric field, that's pointing perpendicular to my DS vector. So what that means is that in this section, the E dot to DS is always equal to 0, right? Meaning that there's no potential difference between this point over here, oh shoot, oh my God, right? There's no potential difference between this point and this point because everywhere along that path, your E dot onto DS is equal to 0. But uh, when I go from this point over here to this point over here, right? I can draw the ds and the e, right? So this will be like, for example, if I'm looking over here, this will be the direction of my ds. So it's pointing radially outwards, but my electric field, that's also pointing radially outwards. So this e dot to ds, it's not 0 anymore. So which means that if I'm looking at the potential difference between here and here, there's going to be a non-zero potential difference. So you should always keep in mind that when you're writing the integral for the potential difference, the e and the ds or like dr or like whatever dx that you use, both of them are vectors and you're taking the dot product between the two. Okay, so now let's just do part C. Calculate the electric potential between the two plates. So I'll redraw it. This is my two plates. And then Okay, so my V, that equals to my negative integral of E dot into the ds. So these two are vectors. Okay, if we just want to find the magnitude of the potential, then it will be positive, right? Okay, so remember, all right, electric field lines. So this is positive, this is negative. They look something like this. So this, and so on. So if I want to find the potential difference between the two plates, so for example, if I want to find the potential difference between a point over here and a point over here, so the easiest path I can integrate over would be this one. So I just integrate along that direction. And the reason why I do that is because if I go along that path, then my E would always be parallel to my ds. So my integral would become E, just scalar multiplication between the magnitude of the E and my like infinitesimal ds. And remember, I found that E is sigma over epsilon 0. So this will be equal to, okay, my integral will be from, if I let this be, right, if I let this be x equals, example, this will be like 0, and this will be 0.01 meters. I know that like this means that the positive x direction would be in this direction, right? Which is okay. Like there's nothing preventing us from making the positive x direction like not what you usually think the positive x direction is, but this just means like we integrate from 0 to 0.01, right? So that means, and also our E is sigma over epsilon 0. So that means the sigma, so that equals to sigma over epsilon 0 times like, from 0 to 0.01, right? So basically, in general, the electric potential between the two plates, that would just be sigma d over epsilon 0. And here our d would be 0.01 meters, and you just plug in we have for sigma and the known constant epsilon 0. So that's our answer to part C. Now calculate the capacitance of this capacitor. Well, okay. I have, actually, let me clear some parts of the screen. So, so we have that the V equals to sigma d over epsilon 0, and I want to find the capacitance, right? Well, so I know that C equals to the total charge divided by V, right? And the total charge, so that's the total charge, which is sigma times the area, and then divided by your V, right? Well, that is times epsilon 0 over sigma d, right? So our capacitance would just be epsilon 0 and then A over D. And again, I believe they're giving you, yeah, they should be giving you the area of each plate, and you just plug in what you got for D and what you got for epsilon 0. And yeah, all right, that's part C and part D. Let's move on to next parts of this question. All right, yeah, E, F, G, H. Calculate the new capacitance of the system with the dielectric between the plates. Okay, so I put a dielectric of kappa equals 2.0 between the two plates. Well, remember, so I have C. If I have a dielectric, then C would be equal to kappa and times epsilon 0 A over D, right? So now it equals to 2 epsilon 0 A and then divided by the D, which means that your capacitance is doubled. And yeah, that's just part E. Electric field strength between the two plates has increased, decreased, or remained the same. So to answer this question, you really need to think about what happens when I place a dielectric between two, like a capacitor, so like two plates. So remember, I have my two plates over here, so plus and minus, and I place a dielectric between the two. So example, the dielectric might like this. And remember, the dielectric, what it is, it's an insulator. So that means that the charges within it are not free to move. But what happens is, you know that like in any material, for example, this insulator, it's composed of many dipoles, which is just like pairs of positive and negative charges. So in this case, like the positive charges in each dipole, it will be attracted to the negative plate, right? And the positive charges will be attracted to the negative plate, and the negative charges will be attracted to the positive plate, right? So if the dielectric was a conductor, what would happen is that I'll have a buildup of positive charges here. So positive, 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 so on, right? And then the negative charges would all go over here. But in real life, what we use as a dielectric, we don't use conductors, we use insulators. So what actually happens is, let me erase these. Yeah, I'll redraw the other plate. So this is my other plate. What really happens is that when I put dielectric in, right? Dielectric, that's an insulator. So instead of the two like the positive and negative charges separating, what happens is that like this is my dipole, like the positive charges, it would for all of the dipoles, they'll all rotate so that the positive charges face the negative side and the negative charges face the positive side. So my dipoles would look like, positive, negative, like positive and negative, and maybe over here it will also look like positive, negative. You get the idea, right? So the positive charges face the positive plate. Sorry, positive charges face the negative plate, and then negative charges face the positive plate. And what this does is, okay, it creates an electric field. The dielectric creates an electric field in this direction, that direction, right? So over here, pointing towards the right. But if you remember, the electric field due to the two plates, that's pointing towards the left, right? So if I have an electric field, originally without a dielectric, electric field, like I only have one electric field, and that's due to the two plates. So it will be pointing towards the left. But now when I put a dielectric in, I have a new electric field generated, and that points towards the right. So what this does is it decreases the electric field strength. So this is my answer, decreases. Now what does this do? Okay, if I look at the electric potential between the two plates, it has increased, decreased, or remained the same. Well, remember, I have like, V in the absolute value of V, that's going to be E and then like uh dot onto the ds. Now my E has decreased, and what that does is it decreases the V. So that's what it does. And now, okay, first, okay, before we go on to part H, what does this do? Okay, so I know that what does this do to the capacitance, right? So I know C equals Q over V. Now Q stays the same, but V, it decreases because my electric field decreases. And if V is on the denominator, right, it decreases, meaning that the capacitance increases. So what does this mean? It means that if instead I fix the voltage, then that means the Q would have to increase. And what that means is that if I put a dielectric in between a capacitor, the capacitor is able to store more charge, which is why like we use dielectrics in real life. Okay. Now the energy stored in the capacitor, what has happened to it? Well, remember we had the energy stored equals to 1/2 CV squared, and it also equals to 1/2 QV, and also equals to 1/2, let's see, 1/2 q squared divided by c. And now, okay, so wait, first, if I look at this one, I'm not really able to get a definitive answer because like my c has increased, but my v has decreased. But if I look at example 1/2 qv, well, okay, q stays the same, but v, it decreases, and this is equal to energy, right? These are all equal to energy. So what this means is that the energy stored in the capacitor has decreased. Okay, so that was a pretty long problem. So it might have been a bit hard to understand, but just remember to go over this problem because it's a really comprehensive review of capacitors, and I believe this is a past AP problem. So if you want to be really prepared for the AP exam, I definitely highly recommend doing this problem again on your own. Other than that, does anyone have any questions on this problem? Like, don't be ashamed to ask, because if you have a question, it means that other people also have questions. I'll give you guys maybe 30 seconds to think of some questions, or like just think about this problem, and then I'll move on. Okay, if no one has any questions, then I'll move on to our lesson. So this next part I, I think I'll go over it when we learn more about circuits, because it requires a bit knowledge about circuits. So you can do it on your own because it is solvable with our current knowledge, but I'll just go over it again when we learn about circuits. So, all right, today, we're gonna start learning about magnetism. So before we were learning about okay, we're learning about magnetism, right? So it consists of electricity, right? The electric, like about electric fields and electric force and stuff. Now we're going to learn about the second part, which is about magnetic fields and like magnetic forces and everything about magnetism, right? So we're going to be starting like the second chapter, like the second, sort of like the second half of electromagnetism. All right. So you know what magnets are, right? Because you probably have them like, at home, or you've seen them before. So magnets, what they consist of is they consist of north poles and south poles. So you might have seen on the magnet, like one end they label it north, and over here on one end they label it south. And yeah, so opposite poles attract. So the north pole always attracts the south pole. So if I had another magnet over here, um, like this was my second magnet, and this part was south and this part was north, then these two magnets will be attracted to each other because the north and south are attracted to each other. And at the same time, the same poles repel. Might be thinking, okay, these two, the south and the south pole, they repel, right? And the north and the north pole, they repel. Why do they still attract? Well, later we'll find out that just like in the electric field, if two poles are farther apart, uh, there's a smaller repulsion than if the two poles are close together. So, but we're getting a bit too ahead of ourselves. But all right, so same poles repel, opposite poles attract. It's just like in like electricity, you have two charges. So you have a positive charge and you have a negative charge. Well, these two charges will be attracted to each other. And if you have like charges, they'll be repelled to each other. So it's just like that in when you're looking at magnets. Uh yeah. it's similar, very similar to charge. You'll see there will be a correlation later. North pole of the magnet generally points towards Earth's north pole. Yeah, we'll get into that in a bit. It's actually a bit confusing and a bit counterintuitive. But yeah, so let's just go on to the next slide. You'll learn about that in a bit. All right, all magnets, they create a magnetic field. It's similar to an electric field. So for example, this magnet over here, I'm looking at this magnet over here, has a north pole and it has a south pole. And what the field lines look at is the field lines, they'll point away from the north pole and they'll point towards the south pole. So again, if we look back at electricity, right? Electricity, like the field lines, they point away from positive charges and point towards negative charges. And that's really similar to north and south poles here. Okay, field lines, they have no beginning or no end. Yeah, they have no beginning or no end. And yeah, that's just a part about magnetic fields. Lines come out of north poles and go into south poles, just like how electric field lines go out of positive charges and go into negative charges. Magnets, they will point in the direction of the field. So yeah, so you can start seeing how there's a big similarity between um like what we learned about electric fields and we will learn about magnetic fields. Later you'll find that there are actually a lot of differences between the two, but like just right now we can see that there are a lot of similarities, like the directions of the field lines and um yeah, like the how positive and negative charges attract, just like how north and south poles attract. So uh yeah, let's go on to the next one. Earth's magnetic field. So what's interesting about Earth is that, in Earth we have a north and a south, right? But if we're looking at the magnetic field, the geographic north pole is actually the magnetic south pole. And the geographic south pole is a magnetic north pole. And also the uh the geographic poles and the magnetic poles, they're slightly off axis. So uh they're not exactly parallel to each other. Every 1,000 to million of years, the poles will switch direction. So in a very, very long time away, we'll have that the geographic North Pole will be pointing in the same direction as the magnetic North Pole, and geographic South Pole will be pointing in the same direction as the magnetic South Pole. But currently, like the north and the North Pole of the magnetic field of the Earth and the North Pole of like the actual Earth, like the geographic North Pole, uh, they're like they're in opposite sides of the Earth. Yeah, field lines are not parallel to the ground. Um, they look also the field lines will look something like this. So you can see on the diagram, and it looks really similar to if you had a magnet over here and the North Pole is pointing towards the geographic South Pole, and the South Pole is pointing towards the geographic North Pole. And it's just like the magnetic field of like a magnet. Yeah. Anyone have any questions on these slides? All right, I guess not. So I'll go on to the next slide. Wait, are these magnetic field line diagrams correctly drawn? Okay. Let's see. I'll give you guys maybe 1 or 2 minutes to think about this problem. It'll really test your conceptual understanding of what we were just talking about. So yeah. All right, so Tony's asking, what does the gray dot in the first diagram uh mean, right? And oh shoot, sorry. I just revealed the answers. Okay. Well, wait, what does the dot mean? Well, that's actually what makes it wrong. What makes like uh the first diagram wrong because no, we can't like basically the dot it should represent like a source of the magnetic field, but remember there's no source or end of the magnetic field. So in reality, this gray dot over here that we draw, like a source of the magnetic field, that doesn't actually like it doesn't exist in real life. So that's what makes the first diagram wrong. Also, Tony, very, very good question. Uh, that's exactly pinpointing what's wrong about the first diagram. So for second and third diagrams, I'll give you guys maybe 30 more seconds to think about that. And yeah, we'll go over it in a bit. And if you have any answers, just send them to me in the chat. And I'll give you feedback. All right, let's go over it. Uh, Tony, could you explain your reasoning for parts 2 and parts 3, like the second and third diagram?
Yeah, okay, so for part two, it's wrong because if you look, there are lines extending out of the south end of the magnet, which is indicative of something going wrong. And for part three, it's correct because all
Actually,
the
actually, wait, pause there for a second. I'll let you explain part 3 in a second, but like, let's go for part 2 first. Uh, so so on the diagram, it's saying it like we see that there are lines going from the North Pole, and seems like there are also lines right. Okay. It also seems like there are lines going from the South Pole, right? So uh right, the reason actually yeah, so what Tony's saying is correct. So he's saying that you have lines going out from the South Pole, right? And that can't be right because the field lines they have to be going they field lines they point away from the North Poles and they point towards the South Pole. And okay, here we have field lines that are pointing away from the South Pole. Um so actually this the second image is wrong because we have field lines that are pointing away from the South Pole. That's absolutely right, Tony. Tony, could you share with us what you think about the third diagram?
I think it's correct because all the lines are pointing in the right direction. The north is pointing outwards and the south are pointing to.
Yeah, it's absolutely right. So we have field lines that are they're pointing towards the South Pole, which is correct. And we also have field lines going towards the South Pole over there. And also there are field lines pointing away from the North Pole. So we have this should be no, this should be no, and this should be yes. Yeah. All right. Here's some more conceptual questions you guys should think about. Magnets always point in what direction? A magnet placed at Earth's south pole will point where? My God. All right, all magnetic field lines end at infinity, true or false? Similar poles of magnets attract, true or false? Draw the magnetic field lines on this magnet. Yeah, so I'll give you guys a couple minutes to think about these problems. Yeah, just remember what we were talking about magnets. And send your answers to me in the chat, and I'll tell you whether they're right or wrong. Sorry guys, it seems like my Zoom got disconnected. So let me restart the sharing. Sorry about that. Oh, let's see. All right, let's go over these problems. All right, Matt, let's go on to the next one. All right, so magnets, they always point, all right, so they always point in the direction of the magnetic field. Uh, so yeah, so oh shoot, yeah. And you can think of it as like, you have a chart, or maybe you can't think of it that way, but just remember magnets, they'll always point in the direction of the magnetic field. Uh, yeah, you'll find later that if it's not pointing in the direction of magnetic field, there will be like a torque that makes it turn into the direction of the magnetic field. A magnet placed at Earth's south pole will point. All right, let's think about this. So we have our Earth, Uh, so this is our Earth. And then remember, over here, it's pointed at the South Pole, right? So the South Pole, right? The South Pole of the Earth, that's the geographic South Pole of the Earth. That's the magnetic North Pole. So this will be as if I have like, this is the North Pole of the magnet, right? If I place a magnet over here, okay, if I place a, let's change the color. So this is my magnet. Then, the South Pole will be attracted to the North Pole, right? So it'll be like South and North. So the magnet will be pointing towards the geographic North because the geographic South of the Earth is the magnetic North Pole. Right, all magnetic field lines end at infinity. No, that's not true because the magnetic field lines, they always point from they point from the north poles to the south poles. Also, similar poles of magnets attract, that's false. They actually they repel, okay? It's like in the electric case, where you have like charges they repel, opposite charges they attract. Now draw the magnetic field lines on the magnet. Well, okay. So, there's it's just like you'll find that it's really similar to if you have like one, okay, let me can think of it as if like draw sort of like sloppily draw analogy towards the electric case. North and south pole, it's as if you have like a positive charge and a negative charge. But you'll see that there's no such thing as like an isolated magnetic charge. So like this is a really it's a bit hand wavy right now, but basically you'll find that the electric field lines will look something basically like what it looks like on the diagram. So you have field lines that go away from the North Pole, but because there's also a South Pole over here, they'll be curling in the direction of the South Pole and they'll go in the South Pole. Inside of the magnet, it'll be you'll find that the magnetic field lines they'll be pointing like from the South Pole to the North Pole. Yeah. All right, moving charge. Oh, before we get to that, I just want to go over a bit more conceptual stuff. So, all right, so first thing is uh if I have like my first thing is that there's no such thing as an isolated North Pole or an isolated South Pole. Like all magnetic poles, so for example, like I have a magnet, right? And it consists of a North and a South Pole. There is no way for me to separate these two poles because on the magnet they might paint it as like they'll paint this part as red and they'll say that's the north pole, and they'll paint this part as blue and that's like they say that's the south pole, right? They're not wrong, right? uh so you have a north pole and you have a south pole, but the thing is if I cut this magnet into two with like a knife or something, I'm not able to end up with two, like I'll end up with two pieces, right? But these two pieces, I'm not able to have like an isolated South Pole here and an isolated North Pole here. That's just a fundamental fact of our universe. There are no isolated like North Poles or isolated South Poles. North and South Poles, they always come in pairs. So if I cut this magnet into half, this is not what happens. I don't get like a separate North Pole and I get a separate South Pole. What actually happens is that I get like I'll cut it in half and this is one piece, this is the other piece, and it'll turn into two magnets. So each of them will have a North Pole and a South Pole and North and South. And you can try this at home. If you cut a magnet into two, you'll end up with two magnets and they each have a North Pole plus a South Pole together. There are no isolated North and South poles. Yeah. All right, next part, the moving charge. What causes magnetism? So there was a guy called Oersted, and in 1820, he discovered that a current carrying wire deflects this compass. In other words, if I have a wire, that'll create a magnetic field because it would, I originally had my Earth's magnetic field, if I have a wire, that produces a magnetic field. So like the total magnetic field is not the same. Like that will not be just the Earth's magnetic field. I'm seeing some questions in the chat. Let me open them up. All right, what about a spherical magnet? Will it have two hemispheres for the poles? Yeah, that's a great question. So yeah, exactly. So if I have a spherical magnet, so how do I make a magnet, right? So you'll learn that there is something called magnetization, and it's like, so what happens is, inside a magnet, uh, it consists of like, like atoms, right? And they have like electrons and like they have electrons, right? And what causes something to become magnetized is like there's a certain like magnetization comes from a certain arrangement of electrons and their own spins. So that's a bit it's a bit quantum mechanical, so it's really hard to explain it with like classical theory, but you'll find that um if I magnetize a sphere, then it will be as if like I have a North Pole up there and a South Pole over there. Like if I magnetize it that way, I can also magnetize it like I can also magnetize it like I have a North Pole over here and the South Pole over there. That doesn't matter. But yes, if I have a spherical magnet, then it will have two hemispheres for the poles. And yeah, that's a really good question by Tony. Uh yeah, that's really good thinking and like shows your creative mind. So yeah, I applaud you for that. Uh yeah. All right, so let's go back to what causes magnetism. So if I have a wire, that'll actually produce a magnetic field. And the reason for that is, if I have a wire and it has current in it, that means there are charges that are moving through the wire. And we'll find that moving charge is the cause for all magnetism. If I have a charge over here and it's stationary, it will not produce a magnetic field. But if I have a charge and it's moving, then that will create a magnetic field. How do I determine the direction of the magnetic field? Well, it's using something called the right-hand rule. So here, in this diagram over here, I have a charge and it's moving towards the right. Now, how do I find the direction of the magnetic field? Well, okay, all right, I hope you guys can see this in my camera. So I have my charge which is moving this way, right? So say it's moving that way. To find the direction of the magnetic field, I'll curl my other fingers to make a thumb, right? Like the thumbs up symbol, but just sideways. So my thumb will point in the direction of the charge velocity, and I'll curl my fingers. And notice the way my fingers curl is the same as the way the magnetic field curls. So you guys can try it for uh this case over here. Uh so the charge is moving towards the right. If I then curl my fingers, then you'll find the direction of the magnetic field, which will also be in it will be in circles. And to determine the direction of the circles, I use the direction that my fingers curl in. And that's called the right hand rule. So you guys can try that out on your own. Let's go on. All right. Now there's something called the Biot-Savart law. And what it does is if I have a current and I know like the magnitude of the current, then I'm able to find the magnitude of the magnetic field at some distance away from like the wire. So I is current, dl is some infinitesimal length segment, and remember it's a vector. So if I'm looking at over here, I'm looking at this small segment over here, and the direction of the dl will be the same as the direction of my current. So it'll be the magnitude of the current times an infinitesimal times the infinitesimal segment of length, and that uh the vector of that infinitesimal length segment will be pointing in the same direction as the current. And then it would be the cross product with the unit vector from the point under investigation to the point of the wire and then divided by the distance squared. So it's sort of like KQ over R squared, but not really, because you'll find it's actually pretty different. Mu zero and 4 pi, they're just constants, so they're outside of the integral. And if you you'll find that this actually obeys the right hand rule, because my DL is pointing towards the right, my R is pointing that way. If you do the cross product, you'll find that the B field, the magnetic field, which we call B, by the way, like usually it's convention to call magnetic field B. I don't know why, but that's what they call it. You'll find that over here, it'll be pointing in the direction of into the screen. And if you use your right hand rule, uh, sorry, wait, no, the magnetic field at this point over here will be pointing out of the screen, so towards you. And if you use your right hand rule, you'll find that you're getting the same answer. So yeah, just curl it that way and it's pointing towards you. Yeah, you can use the units of Tesla or Gauss. I believe Tesla is the what's called the SI unit, like the standard unit that you use, but uh people use Gauss a lot because if you use Tesla, uh it's actually like Tesla to get you know if you have a few Teslas, like for example, if you have a 5 Tesla magnetic field, that's a really, really, really big magnetic field. So in ordinary situations, people often use G instead, which is Gauss. Yeah, that's just units. Doesn't really matter that much. All right. Biot-Savart law also works for moving point charges. So remember, before we had the I times dl. Here we have Q times V, and actually I dl equals to Q times V. Those two are equivalent, so this is just an equivalent form of the Biot-Savart law. And it's just for if I have a single charge and it's just moving. All right, here's a problem. A particle with charge -3 coulomb is traveling to the right at a speed of 8 meters per second. Determine the magnetic field at the point 1, 1. Let me write down the formula for the Biot-Savart law for you. So remember, B equals to mu 0 divided by 4 pi and then times Q times the velocity vector crosses the unit vector and then divided by r squared. So take a moment to do this. It's just plugging in some numbers, help you remember the formula for the Biot-Savart law. So just remember this. Give you maybe 30 seconds to do it. Oh, by the way, you don't mu 0, like this one over here, it's just a constant. You can just leave it like that. Like you don't really have to plug in the numbers if you don't want to. Yeah, so this problem, I just plug in the numbers. There's not really anything to it. It's just math. Uh, just remember your formula for magnetic field. So the Biot-Savart law. Just keep that in mind. Let's just go on to the next problem because this one, there's not much to this problem. So next one. All right, yeah, solution. Yeah. So remember we have. All right, so if we draw it, all right, I'll go to a previous slide so I can just illustrate what they're saying. Okay, so I have a charge. Oops. I have a charge. Okay, this is my coordinate system. My charge is at the origin, has charge -3 coulombs. Okay, now it's traveling to the right at a speed of 8 meters per second. And I want to determine the magnetic field at the point 1, 1. So that has coordinate 1, that has coordinate 1, right? Okay, so remember, B equals to mu0 divided by 4 pi, and then times your Q, and V crosses the R cap divided by your R squared. Now, first, these are constants, so you can just leave it like that. What's your R? Well, you're at the origin, right? So R squared would just be 2. Now, main thing is just finding what is your V crosses your R cap. So the velocity is traveling in, let me switch the color. The velocity would be in, this is the direction of your velocity, and the direction of your R vector, it will be, so the R vector would be pointing in this direction, but that's the vector, not the unit vector, because unit vector would be like, the unit vector has length 1. This is just the full vector R. So I want vector V crosses the R cap. So what's the formula for cross product, right? So I know the magnitude of the V crosses the R, that equals to the magnitude of V times the magnitude of R cap, which is just 1, and then times the sine of the angle between the two. So right now, this angle between the two is theta, and that equals to 45 degrees. So from this, you can just find, right? The magnitude of R cap, that's 1, because R cap is a unit vector. So by definition, it has magnitude 1. And magnitude of V is 8, so it equals to 8 times square root 2 over 2. So you should be getting 4 root 2. And then remember times the charge Q, which is -3 coulombs. Now, as for the direction of the magnetic field, that's also really important. So if you use your right-hand rule, right, it seems like your charge is pointing towards the right. So it seems like you should put your thumb towards the right. The thing is, your charge, it's negative. So instead of like it's traveling to the right at a speed of 8 meters per second, you can think of it as a positive charge traveling to the left at a speed of 8 meters per second. Remember, like, I think it was last week we were talking about if you have, like, if this is your wire and you have an electron that's moving, like, towards the right, then your current will be pointing towards, your eye would be pointing that way. It will be pointing towards the left, because although the electron is pointing towards, its velocity is pointing towards the right, and that's equivalent to having a positron moving towards the left. And the current is the direction of the movement of the positive charges, not the negative charges. So just keep in mind that if you use the right-hand rule to find the magnetic field, you'll be doing this and then like that. So your magnetic field should be pointing into the screen. And you can verify that by working out, V crosses R, right? V crosses R would be pointing, so that way, and then, sorry, V crosses the R would be pointing out of the screen, but because you're multiplying by the charge Q, it makes a negative. So your V would be pointing into the screen, not out of the screen. Yeah, so that might have been a bit difficult to understand. So if you have any questions on this, just feel free to message me in the chat. Don't worry if, yeah, just message me in the chat and I'll do my best to answer it. So let's go and see the solution for this problem. Let me delete my drawings. Yeah. Vector, yeah. So you should be getting 6 root 2 times 10 to the -7 Tesla into the page. Yeah, into the page, not out of the page. Okay, let's go on to the next problem. right, circular ring with radius r has current I traveling through a ring. What is the magnetic field at center of the ring? So I'll just quickly go over this because we're almost out of time. So this is our ring, has radius r. We're traveling through the ring. Okay, remember we had another form of Biot-Savart law, which is mu0 over 4 pi, and then times and then our integral will be like I dl, where dl is a vector, and then cross the r cap divided by r squared. And then we're looking at the magnetic field at the center of the ring. So so if I want to do the integral, right, I'll integrate across this entire ring, right, like the wire loop. And what I do is, for example, if I'm looking at this dl over here, this will be my dl, and my dl vector will be pointing like in the direction of the current. So this will be dl vector. Well, my r vector is pointing that way, and that's always perpendicular to dl, because dl is tangent to the circle. This is r cap, or like r. Now, if I do the cross product between r and dl, you'll find that the b would always be pointing upwards, no matter where you are on, no matter where you're investigating on the wire. So this integral just becomes mu0 over 4 pi. And notice that everywhere, the r and the r squared, that's all the same. Like, I'm integrating over the variable dl. So if I integrate over the entire ring, the circular ring, then r squared, it always stays constant. And this cross product is also always constant. It's also always pointing in the vertical direction. So what I get from this integral is just I times the circumference, which is 2 pi times, like, if I say the radius of the ring is big R, so I times 2 pi big R divided by big R squared, I'll be pointing in the positive z direction, so times z cap. So my answer should be mu0 over 2 pi, sorry, mu0 I divided by 2 pi r, and in the positive z direction, so pointing upwards. Now let's quickly go on to the next part. I really gotta go on to, yeah. Let's go slide 23. Yeah, magnetic force. So be our last part, the last slide of the lesson. So all right, we want to find the magnetic force of a charge that is moving through a magnetic field. Okay, so this is my charge. It's moving towards the right. I have a magnetic field that's pointing upwards. Now, there's a force on it, which is called the Lorentz force. And the Lorentz force, how do I find it's basically like the force on a charge that is moving through a magnetic field. And it's equal to the charge, and then you do the cross product between the velocity vector of the charge and the magnetic field. So here, my velocity is pointing towards the right, and my magnetic field is pointing upwards, right? If I do the cross product, you'll find that the force is pointing out of the page, so towards you. And now, if I have an entire wire which has current in it, I can also find the Lorentz force due to that wire. So if I'm looking at if I'm looking at a point over here, right? And I have a magnetic field that maybe it looks like that. It's always perpendicular, or it doesn't have to be perpendicular, but like, all right, I'll just make a new drawing. So I have a wire over here, and then it's containing charge, and let's say the magnetic field is pointing upwards. Then the current is pointing towards the right. So my DL would be pointing towards the right, and my magnetic field is pointing upwards. If I do the cross product, then the force will be pointing out of the page, so towards me. So this is just the Lorentz force for a magnetic field. Lorentz field force if I have current. So what's the force on like an entire wire with current due to a magnetic field? And you can see it's really similar to like what we got for the Lorentz force of just one single moving charge. And that's because when you have a current, it's just you have a bunch of charges that are moving through a wire, and each of the charges experiences their own Lorentz force. And then if you sum up all of those Lorentz forces together, you'll find that this is your formula for the Lorentz force on an entire wire with current. So yeah, remember, use the right-hand rule when you're doing the cross product between V and B. So yeah, let's go on to the next one. I think next few slides, they're just problems, and these problems, I'll assign them. Yeah, they're all practice problems, so I'll assign some of them for homework so that you can have some practice with them. So yeah, today we were learning about magnetism, and I introduced like topics like the magnets and the Earth's magnetic field. Remember, it's a bit counterintuitive. The geographic North Pole is opposite of the magnetic North Pole. Also, remember the Biot-Savart law, which applies to both like currents and also just a charge that's moving through space. And then also like the Biot-Savart law, it gives you the magnetic field generated by a current or a moving charge. Now, the force that a current, like a wire with current, or the force that a charge moving through a magnetic field experiences, we get that from the formula for the Lorentz force, which is just QV cross B or IDL cross B. So I'll post these slides in the homework. Sorry, I'll post these slides in the email I'll send along with the homework. I'll probably send them tonight or tomorrow. Please review the recording and attempt some of the homework problems. And yeah, so I hope you guys enjoyed this lesson. And yeah, that concludes today's class. See you next week. Thank you guys.